gonna win volleyball. Like he's like a track.
Okay.
Is he in high school? Yeah. He's a track.
Okay. So guys, I want to show you guys these graphs. We didn't talk about the graphs yesterday again because we were falling apart, or I was falling apart. We did everything up to this point, right? Yeah. Okay. So again, trying to go back to the graphs. It says the figure shows the graph of g of x. Estimate the derivative of g for each. And I kind of had gotten down here. So the derivative is basically the slope at that point. It's nice of them in this one, though they kind of help you a little bit by drawing kind of a line, the slope of the tangent line at that point. So what we have to do is we go to the line, and this is as easy as it sounds, so like this should not, we probably could have done this yesterday, but again, it wasn't going well. So -4, x is -4, here's where it hits my graph. I'm trying to find the slope of the tangent line at that point. The slope is going to be my derivative. So again, that's how we did the warm-up we did yesterday, looking at the slope from a line. So what's the slope at this point? -1/2, down 1/2. So the derivative at that spot would equal -1/2. Down 1/2. How about when x is 0? Yeah, the slope would just be flat here. So the slope would just be 0. And then at 4, it would be +1/2. So being able to look at the graph, we had a couple, or we have one of those like on our homework, or a few of those on our homework. So you guys will be able to finish those. All right. What's that? So this one, at this point, so -4 would be, and you could write, slope, yep. Yeah, we're finding the slope. The derivative is the slope of the tangent line at that point. So going to our last problem. Again, talking about the derivative now, 2,000 minus 16t squared is a whole lot easier to work with than the derivative, right? What's our derivative going to be for this? Yeah. Remember, so derivative, drop that number in front, multiply it, bring the power down by 1. And then the 2,000 would just cancel. This is our new fast way. We like this. Remember? All right. They're asking for the derivative when t equals 5 seconds. So now we're just putting that value in. So we're going to do -32 times 5. -160. So the question is, so we have to look at the problem, and we never even read the problem really. So the baseball's dropped from the top of a 2,000-foot building to the ground. They want to know the derivative at t equals 5 seconds. What does that mean for like this problem? Like in this real life problem that we're dropping a baseball off a building, what does this mean? What does -160 mean? Close. That would be if you just substituted 5 into this equation. But do you guys remember what we called, like if you flip the page over, I believe. How fast it is going. It's basically the rate of change at that point, so how fast the ball is going at 5 seconds. So if we're talking about feet and then seconds, the ball is traveling at a rate of -160 feet per second. Why is it negative? It's going down, not up. So, now feet per second, I don't really, like we could figure out what that is, miles per hour, but they talk about objects a lot of times that way. This is kind of a physics type question. So that's how fast the ball is traveling towards the ground.
At 5 seconds.
At 5 seconds. All right, so it says is at what time does it hit the ground? So this kind of goes back to what Maria said. So she said it was the height. We want to know when it's going to hit the ground. We're going to find that information. So think about what I said to your suggestion.
Do you set the equation equal to 0?
Yeah, we're going to set the original equation equal to 0 to figure out when it's going to hit the ground. So the 2,000 minus 16t squared, we want to know when that's going to be 0. So when will the height be 0? Because it's h of t. We should be able to solve this, right? Move the 2,000 over, divide by negative 16. So I get t squared equals 125, right? I believe. So about 11.2, and that's what? Seconds, right? It's going to hit the ball at like 11.2 seconds. Did you guys get that when you were solving it? Yeah. So it asks the velocity of the ball at the moment it hits the ground. So like maybe right before it hits the ground, like as it's approaching the ground, how fast is this ball traveling? How are we going to figure that out?
The 11.2 into the derivative.
Yeah, now we take that 11.2 and we're going to put that into the derivative. Because right before it hits the ball's not traveling at 0. When it's like obviously on the ground it's 0. But right before that, as we're approaching that, we're going to take that 11.2 and put it into our equation for the derivative. So the negative 32 times 11.2. And the reason why it actually sped up, it got faster, is because gravity is forcing it like basically to the ground. It's not like it slows down because it knows it's going to hit the ground. It's a ball. And we don't have like a parachute on it or anything like that. It keeps going faster and faster. So actually dropping something off a really tall building is really very dangerous because it gets faster.
Yeah, I can't like dropping like a penny.
Yeah, like it can come out like a bullet almost,
Yeah.
like where it like.
No, I don't think a penny has enough mass to.
No, you don't think so? But like.
I've heard that it can like chip concrete.
Yeah.
If you drop it from like a
Yeah.
top building, like a skyscraper.
Yeah. All right, is this better? Did I
Yes.
redeem myself?
Yeah.
I can still be your teacher. You're not gonna like put in for me to be fired. Okay,
Maybe
good.
not my trick teacher,
What?
just because I don't like trick.
Just fired me as a trick teacher. Okay.
Just because I don't like trick, not that I don't like trick.
I know the other day she wrote, "I hate this class," but now this is done here or something like that. Thanks, Becca.
Yeah.
All right, so we have the rest of the worksheet to finish, but hopefully now it